with Professor Parimala from Emory University, and this is a free talk for graduate students and postdoc.
Thank you. Okay, thank you very much. And so I just plan to introduce a few keywords on the algebraic theory of quadratic forms, which I'll be using in the main talk. Okay, if you have any questions or you want to stop me or ask something else, you're most welcome. So let me just begin with some notations. So for today's discussion, we'll assume that K is a field and characteristic of K is not 2. So because I'm just going to only deal with such fields, so I can as well assume it is true. And so what is a quadratic form? It is a vector space with a quadratic map from V to K, quadratic map, satisfying quadratic map, which simply means that Q of lambda times V is lambda square times QV, lambda in K, V in V, such that we have the associated linearization V cross V to K given by BQ of VW is, I can put a half, doesn't matter, Q of V plus W minus QV minus QW. This is bilinear. This is the condition on the map. Such a Q we call a quadratic form, and since I'm assuming characteristic is different from 2, I can go back and forth from quadratic forms to symmetric bilinear forms. You see that you can change V and W, the form, this BQ does not change. So the passage from quadratic forms to symmetric bilinear forms is both ways. In the case of characteristic different from 2. So basically I want to say that of course you have a natural notion of isomorphism of 2 quadratic forms. If there's an underlying isomorphism of the vector spaces which preserves the form, that can be translated to suppose AQ. Okay, the symmetric bilinear form, you can choose a basis for V and represent it by a symmetric matrix. Okay, given a quadratic form, you have a symmetric matrix. And what does isomorphism of quadratic forms? It leads to congruence of matrices. Suppose AQ is the matrix associated to Q and AQ prime, the matrix associated to Q prime, then for C invertible matrix. So this is a congruence of symmetric matrices. So the isomorphism of quadratic forms is the same as congruence of matrices. So one can stick to matrices, symmetric matrices, to study isomorphism of quadratic forms. Okay, so what I want to introduce is some kind of basic invariants associated to quadratic forms. Some of them are classical, some of them are more recent. Somehow we have obtained the final so-called classification of quadratic forms in terms of the so-called Galva Homology invariance. This is the so-called Milnor conjecture. Before coming to Milnor conjecture, let me just define the classical invariants for quadratic forms. So first, dimension of Q. So obviously, okay, I'm just going to make a blanket assumption that Q is non-degenerate. So I'm just going to only look at this case. This simply means that the associated bilinear form is degenerate, which is the same as determinant of the associated matrix is non-zero. This is the only situation we are going to look at. Okay, so the dimension of the quadratic form is obviously the dimension of the underlying vector space, but it is also an important invariant, dim2. This is just the class of dimension of V mod 2. So you can look at read the invariance mod 2. This I'll denote by dim2, the dimension invariant. And the second invariant I want to discuss is the discriminant of the quadratic form. Basically, the discriminant is simply the determinant of the associated matrix, except that you just attach a sign to this called sign discriminant. And we would like the invariance to depend only on the isomorphism class of the quadratic forms. So if you take equivalence isomorphism classes, the matrices change by A to C transpose AC. So when you look at the determinant, it changes by a square. So this takes values in K star mod K star square. This is the discriminant invariant for a quadratic form. And the third invariant is the so-called Clifford invariant. So to define the Clifford invariant, we have this notion of it takes values in the Brouwer group of a field. So I'll quickly say what is the Brouwer group of a field. This was introduced by Brouwer to study division algebras over the field. And this is a very, very important invariant associated to field, both from the viewpoint of geometry as well as arithmetic. So let me quickly just define the Brouwer group. This is just you take this equivalence classes of central simple algebras over K, simple algebras over K. Central simple algebras are simply forms for the matrix algebras, and so suppose A and B are central simple algebras. What is an equivalence? It is called the so-called Brouwer equivalence. This means that after taking matrix factors over these, they become isomorphic. Suitable matrix factors of these algebras are isomorphic. This is the so-called Brouwer equivalence on central simple algebras. And of course, given any central simple algebra by Wedderburn theory, you know that it is a matrix algebra over a unique central division algebra over the field. So the Brouwer equivalence is equivalent to the corresponding division algebras are isomorphic. This is the equivalence of central simple algebras. And then you form a group on this equivalence classes. Just the tensor product gives an abelian group structure, and this is called the Brouwer group of K. You put a group structure on central simple algebras by using the tensor product operation, and in order to have inverses and so on, you need this equivalence of identifying matrix factors. So this is the Brouwer group of a field, and of course the Brouwer group of complex algebraically closed field is 0, and the Brouwer group of the real numbers is Z mod 2, generated by the classical Hamilton quaternion algebra. Okay, so the Clifford invariant of quadratic forms, this lives in the Brouwer group. So suppose VQ is a quadratic space. So let us look at the Clifford algebra of the quadratic form VQ, which is defined by taking the tensor algebra of V and modding out by the two-sided ideal generated by V tensor V minus QV. Take the value of the form, this lives in the tensor, this is a 2 tensor and this is a scalar. So you take the two-sided ideal spanned by these relations. This is the Clifford algebra of the quadratic form, and this ideal is graded because this is degree 2 and this is degree 0. So the quotient gets a Z2 gradation. This is C0 of Q, C1 of Q. It gets natural Z2 gradation. And so what is the Clifford invariant? So if dimension of Q is even, then you define the Clifford invariant of Q to be the class of the Clifford algebra in the Brouwer group of K. So if the dimension of the form is even, we know that the Clifford algebra itself is a central simple algebra over the base, and you define its class to be the Clifford invariant. These Clifford algebras come naturally with an involution. So these classes belong to the 2 torsion of the Brouwer group of K. And if dimension Q is odd, then you define the Clifford invariant to be the class of the even Clifford algebra of K, which in this case is a central simple algebra, and its class in the Brouwer group of K is defined as the Clifford invariant of K. So basically, this you could list as classical invariants for quadratic forms, namely the dimension, the discriminant, and the Clifford invariant. And in fact, why they are called classical? In fact, if you take K is a number field without ordering, then in fact these invariants, these 3 invariants, dimension, discriminant, and Clifford invariant, completely determine the isomorphism class of a quadratic form. Okay, these are sufficient to determine isomorphism classes of quadratic forms over number fields. Classical invariants determine quadratic forms, I always mean the isomorphism classes. Okay, these invariants are sufficient. Okay, why I said number fields without ordering, or the so-called totally imaginary number fields, because if the field has ordering, then we need to also take into account the so-called signature invariant. So the classical Sylvester signature over reals comes down to signature invariants over number fields, and you have to put them together with classical invariants to completely classify quadratic forms over a number field. Okay, in the early 20th century, basically the quadratic forms were studied with a viewpoint of arithmetic, or possibly maybe in the context of geometry, study of manifolds or something, but whatever. So people didn't think far ahead in terms of more invariants for quadratic forms, because they're very happy to get a complete classification of quadratic forms. You're just using the classical invariants. But it was in the 30s that Witt, so 1930s, so there was this Witt. So he was interested in study of quadratic forms for general fields. So he introduced the Witt group of a field, Witt ring, I will say, Witt ring of a field K. So this the definition of, see, just as Brouwer introduced the Brouwer group to study division algebras, Witt introduced the Witt group to study quadratic forms, the structure of quadratic forms over a field. So Witt group is constructed from isomorphism classes of quadratic forms, and then you just take the sum of two quadratic forms. You take VQ and V prime Q prime, you can take the direct sum of V and Q prime and sum up the two forms Q and Q prime. That is called the orthogonal sum of quadratic forms. So with respect to the orthogonal sum, which is just taking the direct sum of the underlying vector spaces and adding the two forms. So this with respect to orthogonal sum, and you also need an equivalence, two forms, just as we needed an equivalence for the Brouwer group, you need an equivalence on quadratic forms. This is called the so-called Witt equivalence of quadratic forms. You say that Q is equivalent to Q prime if, so just as in the case of algebras, the matrix algebras are the trivial factors. Here the so-called split forms, that is, you take 1 minus 1, this is the most trivial quadratic form in the study of algebraic theory of quadratic forms. This is called a plane, and you can take some number of copies of a plane. These are the so-called hyperbolic planes. And the real thing you notice about the form 1 minus 1, it is simply x squared minus y squared. It represents 0 non-trivially. Okay, this is the basic fact we notice about such planes. So the equivalence says that after adding such trivial factors, the forms are isomorphic. And after throwing in some hyperbolic planes, if the forms are isomorphic, then you say they are Witt equivalent. So you just take Witt equivalence classes of forms and introduce the operation of direct sum. This gives a group structure. This is the Witt group of a field. Okay, this is the definition of the Witt group. And of course, there you have an important ideal IK, which is just the I can't talk of ideals. I just said it is a group, but you can introduce a ring structure by tensor product of, you can take tensor product of two bilinear forms, there's no problem. So the tensor product induces a group structure on the Witt group. So with respect to orthogonal sum and tensor product, this is a commutative ring. And so you have a basic ideal here, namely consisting of all even dimensional forms. IK is the ideal of even dimensional forms. And this is the notation among quadratic forms people. In of k, this denotes the nth power of this ideal. They just write it this way. Ink is the nth power of this ideal. So you have a filtration on the Witt group, and in fact the Milner's conjecture says that you can just study the associated graded for with respect to this filtration on the Witt group In n greater than or equal to 0. I0 is the whole with group. You can study this filtration via Galva cohomology. This is the content of Milnor conjecture. So let me just quickly define what is Galva cohomology. So I'm just going to define mod 2 cohomology because that's the only thing I'm going to use today. So these are the cohomology group Hn. These are profinite cohomology groups. Hn of a field with values in Z mod 2Z. This is not the usual cohomology, but this is just the cohomology, the profinite cohomology of the Galva group of the separable closure of K over K. K bar is separable closure. Okay, you take the Galva, absolute Galva group. This is a profinite group, and this is a discrete Galva module. And you take the continuous cohomology with respect to that, which you can also think of as direct limit of the usual finite cohomology groups of finite Galva extensions of K with values in Z mod 2Z, where L is contained in K bar and L over K finite Galva. So once you reduce it to finite Galva, these are the usual cohomology groups, and then the limit is the Galva cohomology group, which is defined as the direct limit of these groups. Okay, so this H naught K Z mod 2, this is just the invariance is Z mod 2Z, and H1 K Z mod 2Z, this is just K star mod K star squared. So this comes from the so-called Kumar sequence. You can look at this exact sequence, K bar star. These are these are sequence of Galva modules. The kernel is mu2, which I simply write as Z mod 2 because there is no Galva action. So if you write down the Galva, the long exact sequence, somewhat long exact sequence with respect to this, you get at the H1 level, the H1 is isomorphic. This is called the Kumar isomorphism to K star mod K star squared. And H2, Z mod 2Z, this is just the 2 torsion of the Brouwer group of K. So you have the description of the Brouwer group of K in terms of Galva cohomology. This is H2 of K with values in K bar star. The GM, H2 GM is the Brouwer group. So what you get is the 2 torsion of the Brouwer group of K. So these groups, I mean, when you look at the right hand side, these are exactly the groups where all the classical invariants for quadratic forms live, correct? So the Milnor conjecture so he proposed based on building up on these invariants, he just defined successive invariants for quadratic forms with values in further Galva cohomology groups and said these essentially classify quadratic forms. So this is the content of Milnor conjecture. To be precise, I just want to say I defined the nth power of the fundamental ideal here. So I want to remark that INK has some nice set of generators. Is generated by this is so-called n-fold Pfister forms. So these are forms like 1 minus A1, tensor product of binary forms, 1 minus AN. You take tensor product of binary forms of this shape, then you call it a n-fold Pfister form. I mean, the Pfister brought in these forms to prove several, he developed this whole theory of Pfister forms to solve several important questions pending at that time in the 60s concerning sums of squares and so on. These forms generate the nth filtration of the bit group. Okay, so Milnor had the following conjecture. So you have a map. Even the existence of a map is conjectural. The nth Galva cohomology group, which because IN is generated by Pfister forms, it says that there exists homomorphism En satisfying on Pfister forms. He prescribes what it should be: 1 minus A2 tensor 1 minus AN. This is just the cup product. Okay, I just wanted to say that H1 is just the square classes And for A in K star, let me denote the square class of A by this element in H1 K Z mod 2. This element gives an element in the H1, so you can take cup product of these elements, AN. So you get an element in Hn. So Milner says there is a homomorphism like this which carries this fist of these generators to this. This extends to homomorphism. Further, En is surjective and kernel of En is the next filtration. So this is the full content of Milner conjecture in the quadratic form version. Namely, there is a Milner homomorphism which has this specification on symbols. This is surjective and the kernel is the next filtration. Okay, now this is a theorem. Of course, the Milner conjecture for K theory is due to Vygotsky, but the quadratic form version, which is not an immediate consequence of the K theory version, this is due to Orlov, Wyshik, Vygotsky. So this is the theorem of I'll just refer to this OPV. So this is a powerful theorem because it says the successive gradation of the group is the same as the graded Galva homology ring. So how does it lead to a classification? I just want to make one remark that if you take intersection of all the ideals in IN, this is very classical, the so-called Arison-Pfister-Hopf sorts. It says that the intersection of all the filtration is just the zero ideal. So you just keep, therefore you can say that quadratic forms are classified by Galva homology invariance. But if you want to get more precise arithmetic information about quadratic forms over a field, using this classification via Galva homology, so we need to understand the Galva homology groups better. Okay, so because of this Milner isomorphism, what do you know about generators for H and K? Okay, because In is generated by Pfister forms, and Pfister forms map to such elements A1 cup, A2 cup, An, which you can call symbols. Okay, cup product of N one symbol, this you can call symbols. So because this map is surjective, we know that Hn is generated by symbols. Okay. So this is a non-trivial consequence of Milner conjecture, which is now a theorem. But what I will use in the next talk is that how important it is to understand how the Galva homology is generated by symbols, how efficiently it's generated in order to make specific conclusions about the nature of quadratic forms, whether they represent zero or not, etc., etc. You need more information about the Galva homology. So maybe I will leave with an exercise that suppose K is a field, all characteristic, H3 is 0, say. And suppose every element in H2 is a sum of at most two symbols. E is a sum of two symbols. Less than or equal to two symbols. Suppose this happens, then you can conclude that every seven-dimensional form, quadratic form over K has a non-trivial zero. At most, you can have six-dimensional forms which are anisotropic. So this is an easy exercise which one can just do it with hands using quadratic forms. But we'll discuss in the next talk more efficient generation for such kinds of function fields. Any question? Yeah. Okay, I was in a hurry because or an algebraically closed field, every form you can diagonalize. That is the very important fact. You can diagonalize the form. Only square classes matter. So 1 minus 1 is trivial in the Witt group. So you can take out, and so you may end up with rank 1 form at most. So it is Z mod 2. The dimension is the only invariant Z mod 2. But more interestingly, over real numbers, the signature is the only invariant. Signature is in Z, and in fact, Witt group of real numbers is Z. And all of class field theory is about okay, the Brouwer group and so on, which in particular gives some kind of hold of the Witt group of number fields and things like that. Any other question? Okay, so thank you for listening. So.